Japan is once again on edge after a powerful earthquake. But what has scientists and emergency officials watching especially closely is the aftershock pattern now unfolding. It is not behaving in the most expected way, and the next 72 hours could be critical for understanding what comes next. In this update, the focus stays on what is known, what remains uncertain, and why this short window matters so much. If careful, science-based coverage like this is helpful, please like the video, subscribe to the channel, and stay with us for the full update. Far to the east of northern Japan, the Pacific Ocean stretches in a long cold plain that seems calm from above. Its surface rises and falls with weather, with wind, with distant swells, and with the steady breathing motion of water across the seasons. Beneath that open water, however, the earth remains in motion at a pace too slow for daily life to notice, and too large for any city or shoreline to resist. In this wide outer setting, the earthquake off northeastern Japan belongs not to a single moment alone, but to a plate boundary that remains active across immense spans of time. The present update begins here, at the broadest scale, where the sea floor, and the edge of the continent meet in a long arc of strain. Japan stands near one of the most complex plate boundaries on Earth. To the east lies the Pacific Plate, a vast slab of oceanic rock that moves generally westward. Along the northeastern side of Honshu and toward Hokkaido, that oceanic plate descends beneath the landward plate at the Japan Trench. A trench is a long, deep depression in the seafloor formed where one plate bends and sinks below another. The feature is narrow compared with the ocean around it, yet it marks one of the sharpest boundaries in the outer structure of the planet. At the surface, the trench is only a line on a map or a change in seafloor depth. In the deeper frame of the Earth, it is a moving contact zone between great slabs of rock. This motion does not happen in a smooth and constant slide. The plates attempt to move, but friction holds parts of the boundary in place for years, decades, and sometimes longer. While that contact remains locked, strain accumulates in the crust and uppermost mantle around it. Strain means slow deformation, the gradual bending or loading of rock under stress. The stored energy does not vanish. It remains within the plate boundary system until some part of the fault slips. When that release happens suddenly, the motion sends seismic waves through the earth and across the sea floor, and an earthquake enters the human record as a single event. Yet the event itself is only the visible part of a much longer physical process. Off the Pacific coast of northeastern Japan, this system has produced many large earthquakes. The region is well known to seismologists because the Pacific Plate descends rapidly, and because the boundary has repeatedly generated powerful shaking and tsunamis. The Great Earthquake and Tsunami of 2011 remain the most widely remembered example in recent history, but the tectonic setting is older and broader than any one disaster. The plate boundary does not reset into stillness after a major rupture. It continues to move, continues to store strain, and continues to adjust. Each new earthquake occurs within that persistent setting. The current earthquake sequence near Miyako, offshore from northeastern Honshu, fits this wider pattern. Official analysis identifies the main shock as thrust faulting near the subduction interface. Thrust faulting means one block of rock pushes up and over another under compression. In this part of Japan, compression develops because the oceanic plate presses beneath the landward side as it descends. That broad mechanical setting matters because it shapes both the main shock and the sequence that follows it. It also explains why scientific attention settles quickly on the surrounding offshore region after a major earthquake there. The sea may appear open and empty, but the plate boundary below it is crowded with stress. The landward side of this boundary is not a rigid wall. Northeastern Japan deforms gradually as it absorbs the long push from the Pacific side. Parts of the coast may rise or sink over geologic time. Sediments accumulate in offshore basins. Older faults within the crust remain present, even if they are not always active. Mountain belts farther inland record earlier phases of compression and uplift. All of these features belong to the same regional system, in quiet periods. They seem separate from one another. During a significant earthquake, their connection becomes clearer. The broad plate motion provides the outer framework within which local ruptures occur. This outer setting also helps explain why the coming 3 days receive such close attention in public guidance. In undersea earthquake sequences, aftershocks can remain active for a period in which additional strong shaking is still possible. Japan Meteorological Agency guidance notes that undersea events often require particularly careful watch through the first several days, with the largest aftershocks in such marine settings tending to occur over a slightly longer early window than many inland sequences. That does not mean a larger event will happen, and it does not allow certainty about timing. It means only that the offshore tectonic environment and the statistical behavior of similar earthquakes make the early period especially important for caution, monitoring, and repeated reassessment. The phrase unusual aftershock pattern should be understood carefully in this broad context. It does not mean the laws of plate motion have changed. It does not mean the Earth has become chaotic or unreadable. It means that within the familiar tectonic setting, the current sequence does not follow the most ordinary short-term decline in activity with perfect simplicity. Observations indicate a sequence that demands close measurement and comparison with prior offshore earthquakes in the same region. The wider plate boundary still behaves as a subduction zone behaves. The uncertainty lies in the detailed rhythm of release within that known structure, not in the existence of the structure itself. Across the outer Pacific margin, instruments on land and sea continue to record this shifting system. Seismometers detect the small and large motions that travel outward from the source region. Tsunami gauges and coastal observations help confirm how the sea surface responds. Agencies compare the present sequence with earlier ones, not because history repeats exactly, but because repeated earthquakes within the same plate setting reveal common tendencies. The boundary offers patterns, not guarantees. It gives scientists a physical framework strong enough to guide warning and analysis, while leaving room for local variation that only fresh observations can resolve. So the story begins not with a town, a harbour, a damaged road, or even a single rupture plain, but with the wide Pacific margin east of Japan. There, the ocean covers a moving plate. There, the trench marks descent into the earth. There, strain builds slowly under the sea beyond the horizon of ordinary sight. In that broad outer region, the current earthquake update takes shape as part of an active subduction boundary that remains one of the most closely watched on the planet. The sea above it remains wide and grey. The crust below it remains under compression. The sequence now unfolding belongs to both. East of Miyako, beyond the visible line of the coast and beyond the harbours, roads, and seawalls of Iwate Prefecture. The earthquake begins in the offshore source region. This is the part of the event that remains hidden from direct sight, yet determines much of what follows at the surface. The sea above appears broad and undisturbed except for weather and ordinary swell, but below it the rocks of the subduction zone are under compression. In this section, attention stays with that offshore setting alone, where the main shock takes shape near the plate boundary and where the geometry of the rupture starts to explain the pattern now under study. The current main shock lies well out in the Pacific, roughly 100 kilometers east to east-northeast of Miyako, at a depth of about 35 kilometers. That depth places the rupture below the seafloor, but still within the upper part of the plate boundary system where strong earthquakes commonly occur. It is not a deep earthquake far down within the sinking slab, and it is not a shallow crack at the immediate seafloor surface. It occupies an intermediate position within the offshore tectonic structure, in the zone where the descending Pacific plate and the overriding crust remain mechanically linked by pressure and friction. The focal mechanism, which is the scientific reconstruction of fault motion from seismic waves, indicates thrust faulting. In simple terms, the rocks on one side of the fault move upward relative to the other side under horizontal compression. This is the expected style for a subduction boundary like the Japan Trench margin. The Pacific plate drives westward and downward. The overriding side resists, bends, and stores stress. When failure begins, the motion releases part of that stored energy in a sudden shift. The offshore source region is therefore not random in shape or style. It fits the long-known mechanical behavior of the northeastern Japan subduction zone. This region beneath the sea is not a smooth plain. The boundary between the plates includes rough patches, sediment layers, bends in the incoming oceanic crust, and places where friction differs from one segment to another. These variations matter because earthquakes do not rupture every part of the boundary in the same way. Some areas remain tightly locked for long periods. Others slip more readily or creep so slowly that they release strain without a large quake. Between these extremes are patches capable of sudden failure. The source region of the present event appears to belong to one of these stressed offshore patches, large enough to produce a major earthquake, yet still part of a broader fault system that extends far beyond the edges of the current rupture. When seismologists locate a main shock offshore, they look not only at the epicenter, which is the point on the Earth's surface directly above the rupture origin, but also at the full rupture area. The epicenter gives a useful reference, yet the earthquake itself occupies a volume and a plane, not a single dot. Rupture begins at one point and then spreads across part of the fault surface. In a large offshore thrust earthquake, the spreading motion may extend across tens of kilometers in a matter of seconds. The energy released along that plane shapes the pattern of shaking, the distribution of smaller later events, and any sea surface disturbance produced by vertical movement of the seafloor. The present source region appears close enough to the trench system to fit the subduction interface setting, yet not so close to the outermost trench axis that every part of the rupture would be expected at the shallowest sediment-covered edge. That distinction matters because the exact place where slip concentrates affects both tsunami efficiency and aftershock behavior. Very shallow rupture near the seabed can displace water especially well if vertical motion reaches the seafloor strongly. Slightly deeper slip may still generate a tsunami, but often with different proportions between earthquake magnitude and sea surface response. The source region is therefore read not only as a place on the map, but as a three-dimensional zone whose depth and geometry carry physical meaning. The rock of the descending Pacific plate also enters the story here. Oceanic crust forms at spreading ridges, cools as it crosses the ocean basin, and becomes denser with age. By the time it reaches northeastern Japan, it is old, cold, and mechanically strong in some layers, though cut by fractures and altered by seawater over geologic time. As it bends toward the trench, it develops additional stress. As it descends, it carries water bound in minerals and sediments into deeper conditions. These features help shape the physical environment of the source region, even when the main rupture occurs on the plate boundary rather than inside the slab itself. The offshore fault is therefore surrounded by rock that has a long prior history before the earthquake begins. In the current sequence, the first concern in the source region is not only the size of the main shock, but the way the nearby offshore fault network adjusts after the initial rupture. A major thrust event changes the stress on neighbouring parts of the boundary. Some patches become less likely to slip immediately, others are brought closer to failure. This is one reason aftershocks often spread around the main rupture, rather than piling only at the exact point where it began. In an offshore setting east of Miyako, this redistribution happens beneath deep water, across faulted rock that cannot be observed directly in real time. Scientists infer it from the locations, sizes, depths, and mechanisms of the earthquakes that follow. The phrase next 72 hours are vital has meaning here because the offshore source region is still settling into a new stress state after the main release. That statement does not promise a single outcome. It does not declare that another large rupture must happen. It recognizes that the early post-main shock period is when the source region reveals its short-term behavior most clearly. Clusters may tighten, spread, slow, or reappear on adjacent patches. Depth patterns may become clearer as more events are located. The unusual character of the sequence is read first in this hidden offshore field, before it is fully understood on paper. So this second layer of the story remains out at sea, where the earthquake starts beneath cold Pacific water in compressed rock near the subduction boundary east of Miyako. The main shock lies at a depth and in a style consistent with the long-active Japan trench system. Its rupture occupies a fault surface rather than a point. Its setting includes rough plate contact, descending oceanic crust, and uneven friction across the boundary. The aftershocks now under close watch belong to that same offshore structure. In this region, the earthquake is still a problem of rock, depth, pressure, and motion under the sea. Above the offshore source region, the sea responds in ways that are sometimes immediate, sometimes subtle, and often difficult to read in the first minutes after a major earthquake. In this outer layer of the event, attention stays not with the rocks that slip below, but with the water above them. The ocean surface is sensitive to movement of the seafloor, yet it does not mirror every earthquake in the same way. Much depends on depth, on the style of faulting, on how much vertical displacement reaches the seabed, and on the shape of the surrounding basin. In the present sequence east of Miyako, the regional sea surface becomes one of the first places where scientists test early assumptions against direct observation. When a large offshore earthquake begins, warning agencies move quickly because tsunami generation cannot be judged by magnitude alone. A tsunami is a long wave produced when a large volume of water is displaced, most often by vertical movement of the seafloor. The key point is not simply that an earthquake has happened under the sea. The important question is whether the rupture lifts or drops the seabed enough, over a wide enough area, to disturb the water column above it. That is why the first response after a large undersea shock includes rapid modelling, caution in public messaging, and close attention to coastal and offshore gauges. In this case, warnings and advisories are issued early because the earthquake occurs in the familiar tsunami-producing belt off northeastern Japan. That coastal region has a long history of sea level disturbance after major offshore shocks, and the emergency system is designed to treat the first minutes with seriousness. Yet as observation replaces estimation, the sea begins to show its own measured answer. Gauges, tide stations, and offshore instruments report the actual wave heights moving through the region. These values matter because they reveal whether the rupture translated strongly into vertical water motion or whether the sea surface response remains more limited than the first cautionary picture might suggest. The difference between forecast and observation is normal in tsunami science. Initial messages are built for safety. They are meant to move faster than certainty. In the first phase, the size and position of the earthquake, along with known behavior of the source region, guide expectations. Later, direct measurements refine those expectations. If observed wave heights remain small, warnings may be downgraded or lifted. If the sea behaves more strongly than expected, alerts may be maintained or strengthened. The sequence is therefore a process of adjustment. The water itself becomes part of the evidence. In the regional sea surface around Sanriku and northern Honshu, small changes in level can still matter even when they do not become catastrophic waves. A tsunami does not behave like ordinary wind-driven surf. Its wavelength is long, and in deep water its amplitude may be modest while its speed remains high. As it approaches shallower coastal waters, the wave slows, bunches, and may grow. Harbours, bays, river mouths, and coastal shelves can modify its height and timing. A modest offshore disturbance may therefore arrive unevenly from place to place. One station may show a small rise, another a more noticeable oscillation. The pattern depends not only on the earthquake source but also on the shape of the sea floor and coast. For that reason, regional sea surface response is never read from one number alone. Scientists compare arrival times, peak heights, repeated pulses, and the duration of oscillation. A sea level disturbance may come not as a single crest, but as a series of movements over many minutes or hours. The first arrival is not always the largest. Water may continue to rise and fall after the initial warning period, especially in enclosed or semi-enclosed coastal settings where resonance can amplify later waves. Even when the observed heights remain limited, authorities tend to keep attention fixed on the sea until the pattern clearly declines. In the present event, the observed behavior of the sea suggests a response that is important but not as extreme as the most severe offshore earthquake scenarios in this region. That distinction helps narrow the interpretation of the source. It suggests that while thrust motion occurs, the rupture may not have produced the broad and powerful shallow seabed displacement associated with the largest destructive tsunamis along the Japan Trench margin. This does not reduce the seriousness of the earthquake itself. It simply means that the water column above the source appears to record a more constrained transfer of motion from rock to sea. The calm appearance of the open ocean can be misleading during this stage. Far from shore, the surface may reveal little to the eye, even where instruments detect a measurable tsunami. The wave in deep water may pass with only gentle height change over a vast horizontal scale. The true character of the disturbance becomes clearer only through instruments and coastal response. That is why this region of the story belongs as much to measurement as to direct experience. The sea surface speaks quietly at first, and technology is needed to hear it. This outer water layer also shapes public behavior in the first critical hours. Fishing ports, ferries, seawalls, and low-lying shore facilities remain exposed not only to wave height but to currents. Even a small tsunami can drive dangerous surges in harbours and channels. Boats may strain against moorings. Water can reverse direction unexpectedly. Floating debris can move with force. So when the sea surface is under observation after an offshore earthquake, the concern is broader than a single dramatic wall of water. It includes the slower, persistent instability of coastal water that may continue after the first visible change. Thus, the regional sea surface becomes a quiet testing ground for the earthquake's true offshore character. The ocean above the rupture does not simply confirm that shaking occurred, it helps reveal how the seabed moved, how much vertical displacement reached the water column, and how the surrounding basin transmits that disturbance toward shore. In this section, the sea remains the central region wide, cold, and outwardly restrained, yet full of information. its gauges refine the early warning. Its small oscillations matter. Its measured response forms the next layer of understanding in the hours after the main shock. Along the northeastern coast of Honshu, the sea meets land in a pattern shaped by old uplift, erosion, river flow, and repeated contact with powerful waves. In this region, the coastline is not a smooth edge. It bends inward and outward, forming bays, coves, narrow inlets, fishing ports, river mouths, low plains, and steep headlands. Offshore earthquakes do not arrive at such a coast as a simple and equal force. The same wave can be softened in one place, tightened in another, and turned into fast-moving harbour currents somewhere else. So in this section, attention rests fully on the coastline itself, the outer edge of land where the open Pacific first gives way to human settlement, concrete structures, and narrow strips of working shore. The Sanriku coast, including the coastal districts near Miyako, is especially distinctive because of its deeply indented form. Rias Coast is the geological term often used for this kind of shoreline, meaning a coast where drowned river valleys create long, narrow bays and irregular inlets. Such a shape is beautiful in ordinary light. It also makes the coast sensitive to sea level oscillation. Water entering a confined bay does not simply spread in a wide, shallow sheet. It can be channeled, reflected, and concentrated. Even when a tsunami remains modest in regional observations, local harbour behaviour can still demand caution because the coastline gives the water many ways to accelerate and turn. Miyako and nearby coastal communities face the Pacific directly, yet they do so through layers of local protection and adaptation built over many decades. There are seawalls, breakwaters, raised roads, harbour works, floodgates, evacuation routes, and higher ground marked in public awareness. These structures do not remove risk, they alter it. A breakwater may reduce ordinary wave energy and help shelter a port. A seawall may delay or limit inundation under certain conditions. River mouths may remain vulnerable if water is pushed inland through low channels. Flat reclaimed ground near ports may behave differently from older terraces or steep residential slopes. The coastline is therefore an engineered and inhabited boundary, not only a natural one. In the first hours after a major offshore earthquake, this coastal edge becomes a place of suspended movement. Fishing activity slows or stops. Vessels already at sea may hold position in safer water if conditions allow. Moorings, floating docks, and harbour basins remain under watch. People in low-lying areas may move away from the waterfront not because a dramatic wall of water is already visible, but because the coast can change quickly once long waves begin to enter confined spaces. The shoreline is where warning turns into practical action. It is where a measured disturbance in the sea acquires consequence for roads, piers, storage yards, and the rhythm of coastal work. The shape of the Sanriku coast has long influenced how earthquakes are remembered there. Some locations open broadly to the sea, while others lie at the heads of narrowing inlets. A narrowing bay can amplify water height by funneling energy into a smaller space. Harbours may also experience strong horizontal flow even when vertical rise appears limited. This matters because coastal exposure is not only about flood depth, it is also about force. Fast water can damage moored boats, tear loose equipment, strike quay walls, and move debris. Where a river meets the sea, the oscillation can travel inland for a time, affecting banks and low adjacent land before gradually fading. The coast is also exposed to strong ground shaking before any sea disturbance becomes visible. Ports, bridges, retaining walls, utility lines, and roads near steep slopes can be affected by the motion of the ground itself. Soft reclaimed land may shake differently from bedrock headlands. Hillside roads above fishing towns may experience small falls of rock or soil. Old structures may respond differently from newer reinforced buildings. Thus, the coastline is doubly exposed. It receives both the shaking transmitted through land and the delayed or prolonged movement of water from the offshore source. These are separate hazards that overlap at the shore. Yet exposure is not uniform along the coast. Some districts stand on higher marine terraces, old uplifted surfaces that place homes and public buildings well above the immediate waterfront. Others depend on narrow, low strips of land between hillside and harbour, industrial yards, fish markets, fuel facilities, and transport links are often built close to sea level for practical reasons. This arrangement is efficient in ordinary times, but it binds daily life to the most exposed part of the coastal plain. The earthquake, therefore, brings attention not just to natural shoreline form, but to the geography of human use layered onto it. In the present event, the outer edge of land is watched closely because even a restrained sea surface response can produce meaningful local effects when channeled into ports and inlets. Coastal exposure does not wait for a worst-case scenario to become relevant. It is present as soon as there is uncertainty in the sea and damage potential in the built shoreline. Authorities, harbour managers, and residents all read the coast differently, but they read the same boundary, the line where land, concrete, tide, and warning meet. The next 72 hours matter here not because the shoreline itself changes, but because repeated aftershocks can renew concern, interrupt recovery work, and complicate the decision of when normal coastal activity can safely resume. There is also memory in this region. The coast has known severe earthquake and tsunami disasters before, and that memory has physical and social form. It exists in rebuilt seawalls, in evacuation signage, in schools, in municipal planning, in habits of moving uphill when needed, and in the quiet seriousness with which offshore warnings are received. Coastal exposure is therefore not only a matter of geography, it is a relationship between landscape and preparedness. The shape of the shore teaches caution because it has done so repeatedly across generations. So this section remains at the coastline itself, the first landward region reached from the open sea. Here, the indented Sanriku shore, the ports near Miyako, the river mouths, the sea walls, and the low plains all define how offshore danger can be translated into local consequence. The coast is irregular, worked, inhabited, and historically alert. It is the meeting place of measured wave, damaged infrastructure, and practical decision. On this narrow edge of land, exposure is not abstract. It has harbours, roads, slopes, concrete, memory, and tide. From the exposed coastline, the event moves inward across districts, towns, valleys, and upland roads as surface shaking. This is the part of the earthquake that enters daily life most directly. People do not experience focal mechanisms, trench geometry, or fault planes in the first moment. They experience motion in floors, walls, windows, hanging wires, shelves, roads, and slopes. In this region of the story, the sea is no longer central. The concern is how seismic energy spreads through the land, how it is modified by local ground, and why one place may feel only strong swaying while another nearby place suffers falling objects, cracked walls, or damaged infrastructure. The earthquake becomes a landscape of uneven intensity. When a major offshore earthquake occurs east of northeastern Honshu, the shaking does not travel inland as a single uniform pulse. Seismic waves radiate outward from the rupture and pass through rock layers, sedimentary basins, coastal plains, and mountainous terrain. Some waves move quickly through stronger rock, others slow, bend, reflect, and lengthen in softer material. The result is that intensity, meaning the strength of shaking felt at the surface and its effects on structures and people, varies from district to district even within the same broad region. Distance from the source matters, but it is never the only factor. In the present sequence, the strongest inland effects are expected in the northeastern districts facing the Pacific, especially parts of Iwate and neighbouring areas exposed to an offshore source east of Miyako. Yet even there, the pattern is not simple. Coastal terraces underlain by firmer ground may shake differently from low alluvial plains built of river and marine sediments. Reclaimed industrial ground near ports often responds differently from older natural slopes. Valleys can trap and amplify motion. Small basins may prolong swaying. Ridge tops may respond sharply to certain frequencies. A house on compact ground and a warehouse on soft fill may not tell the same story even when they stand within a short drive of one another. This difference arises because surface shaking depends on local site conditions. A site condition means the properties of the near surface ground beneath a place, whether it is hard bedrock, dense gravel, loose sand, water, rich sediment, artificial fill, or layered combinations of these materials. Softer ground tends to shake more strongly, and for longer periods for some kinds of motion, because it can amplify seismic waves. Harder ground often passes certain waves more quickly with less amplification, though sharp jolts may still be severe. This is why earthquake maps based on instrument readings often show bands and pockets of higher intensity that do not form neat circles around the epicenter. The land itself reshapes the motion. Across northeastern Japan, the built environment also filters the event. Wooden homes, concrete apartment blocks, schools, bridges, tunnels, port structures, and utility lines. Each respond according to their own mass, stiffness, age, and design. A structure does not simply receive shaking, it interacts with it. Short, stiff buildings may respond strongly to quick motion. Taller buildings may sway longer under slower waves. Retaining walls may crack where slopes shift slightly. Water pipes may fail at joints. Road embankments may settle. Rail systems may halt automatically even where damage is limited, because the region's earthquake safety culture treats rapid precaution as part of ordinary response. Surface shaking therefore spreads not only through geology, but through networks of transport, power, water, and communication. The inland experience of shaking also changes with time after the main shock. A strong aftershock can reawaken fear in places that were already inspected and thought to be stabilizing. Damage that seems minor after the first event may worsen under repeated motion. Loose roof tiles fall later. Small wall cracks widen. Already weakened slopes lose a little more support. People who have returned to collect belongings may need to leave again. In this sense, regional surface shaking is not confined to the minute of the main shock. It becomes a repeated condition across the first days, especially when the aftershock pattern does not settle quickly into a simple decline. This is one reason the next 72 hours matter so much inland even away from the shoreline. Emergency managers do not look only for one catastrophic collapse. They also watch for cumulative strain in the built landscape. Bridges are checked more than once. Mountain roads are watched for rockfall or subtle deformation. School buildings, public halls, and shelters are reassessed after new shaking. A district that receives only moderate damage in the first survey may still face disruption if repeated aftershocks keep transport uncertain or prevent safe use of some structures. Surface intensity, in this early period, is part of an evolving picture rather than a single reading frozen in time. Human perception adds another layer to this region. People often report that one shock feels sharp and vertical, another rolling and prolonged, another strangely weak despite similar reported magnitude. These impressions reflect the complex mixture of wave types, local ground conditions, and building response. They also reflect fear and fatigue. After a major offshore event, even moderate shaking can feel more threatening because the body remains alert to recurrence. In communities along the Pacific side of northeastern Japan, that psychological dimension is shaped by long memory as well as present motion. The ground may still the next morning, yet every small tremor carries more weight than it would in an ordinary week. Still, science remains careful in how it interprets these inland effects. Strong shaking in one town does not by itself prove an unusual fault process. A lower than expected impact in another does not mean the earthquake was weak. Intensity must be read together with instrument data, source properties, and local geology. Observations indicate that the current sequence produces a regionally significant but spatially varied pattern of shaking, consistent with a major offshore event whose energy is filtered through the complex ground conditions of northeastern Japan. What remains uncertain in the early period is how much repeated aftershock activity will continue to refresh that pattern across the same districts. So this section remains entirely on land, across the districts that receive the earthquake as motion at the surface. Here the event becomes uneven swaying, jolting, falling objects, cautious inspections, halted transport, and repeated checks of slopes and structures. The shaking is shaped by distance, by sediment, by reclaimed ground, by basin geometry, and by the response of buildings themselves. One prefecture map can show the outline of the event, but only the ground beneath each town tells how the motion is truly felt. In this inland region, the earthquake is no longer a hidden rupture under the sea. It is movement distributed across ordinary places. Across Japan, the earthquake is not watched by a single instrument or a single agency looking at one screen. It is followed through a distributed monitoring field that stretches from offshore cables and seabed stations to inland seismometers, coastal gauges, municipal intensity meters, and the national processing systems that assemble these signals into rapid public information. In this region of the story, the focus remains on those systems above and across the landscape, the observing layer that turns hidden motion into measured pattern. The earthquake is still occurring in rock beneath sea and land, but here it becomes a stream of numbers, wave traces, automatic estimates, maps, alerts, and repeated revisions made possible by dense monitoring. Japan's earthquake observation system is unusually extensive because the country sits in one of the most active seismic regions on Earth and has built its warning culture around rapid measurement. The Japan Meteorological Agency operates a nationwide earthquake observation network and also gathers data from a much larger set of seismic intensity meters managed by local governments and by the National Research Institute for Earth Science and Disaster Resilience. Together, these systems allow shaking to be identified quickly, located, and translated into public information while the event is still unfolding. What reaches television, radio, phones, transport systems, and emergency offices is the visible end of that monitoring chain. A seismometer is an instrument that records ground motion. Some are designed to detect very small movement with great sensitivity. Others are built to record strong shaking without losing accuracy when the motion becomes intense. Japan uses both kinds because a large offshore earthquake produces a wide range of signals. Near the source, the instruments must remain reliable under strong motion. Farther away, the system still needs to capture smaller waves that help define location and sequence. This layered design matters in the current event because the aftershock field includes both stronger shocks that renew public concern and many smaller ones that mainly serve scientific interpretation. One part of this monitoring layer is the earthquake early warning system. It works by detecting the first arriving waves near the source and using them to estimate the earthquake before the strongest motion reaches more distant places. The first waves are faster and generally less damaging than the later. Stronger shaking, that difference allows a brief warning interval, sometimes only seconds, but still long enough for trains to slow, industrial systems to pause, and people to brace or move away from immediate hazards. In an offshore sequence east of Miyako, those first rapid estimates are especially important because the source lies away from the coast, giving some inland areas a narrow but meaningful time window before the strongest motion arrives. Yet early warning is only one part of the observing landscape. Once the main shock is underway, a second task begins immediately refining the event. Initial location, depth, and magnitude can change as more data arrive. This is normal, not a flaw. The earlier solution is designed for speed. The later one is designed for accuracy. Offshore events often require particular care because the source lies beneath water, where the geometry between earthquake and instrument network is less balanced than for an inland event surrounded by dense stations on all sides. Scientists therefore watch the evolving fit between incoming wave data, offshore context, and instrument distribution as the picture sharpens. The National Research Institute for Earth Science and Disaster Resilience adds another crucial layer through its land and seafloor networks. The High Sensitivity Network records small earthquakes in great detail. The Strong Motion networks record damaging shaking at the surface and below ground. The Integrated Observation System also includes offshore monitoring, where seafloor stations help detect earthquakes and tsunamis in real time. These marine observations matter greatly in a sequence like the present one, because the offshore source cannot be understood fully from land data alone. The sea does not permit direct inspection of the rupture, but seabed instruments narrow that distance by bringing the measurement field closer to where the fault is adjusting. This broad monitoring network is also why the phrase unusual aftershock pattern has scientific meaning rather than rhetorical force. A pattern can only be called unusual when it is being measured against a large background of ordinary sequences, using dense and consistent data. The network makes that comparison possible. It shows whether aftershocks are clustering tightly or spreading, whether they are decaying at the expected rate or persisting more actively, whether their depths are concentrated or layered, and whether their focal mechanisms resemble the main shock or begin to diversify. Without such monitoring, people would still know that the ground was shaking. They would not know how the sequence is behaving. Along the coast, tsunami gauges and sea level observations contribute their own stream of evidence. These systems help determine whether the undersea rupture has displaced water significantly, and whether later changes in the sequence alter marine hazard. Their readings are especially important after the first warning period, when the question shifts from immediate emergency messaging to careful confirmation of what the sea is actually doing. The coast and the sea in this observing region become parts of the instrument field rather than passive scenery. They are watched continuously, not only during the dramatic first minutes. Public trust in earthquake information depends on this observing layer remaining both fast and restrained. The networks must be quick enough to issue useful warnings, but careful enough to revise when the early picture proves incomplete. That balance is particularly important in the first 72 hours of an active offshore sequence. Each aftershock tests the system again. Each new event enters the same chain of detection: estimation, mapping, and interpretation. Emergency managers, local authorities, transport operators, and ordinary households all depend on that repetition being steady and credible. The monitoring network does not stop with the main shock. It becomes more important after it. So this section remains within the observing field spread across Japan and its surrounding waters. Here the earthquake is translated into signals, fast waves picked up by seismometers, intensity readings gathered by thousands of meters, offshore motion traced by seafloor networks, sea level changes watched at the coast, and all of it assembled into rapid national information. The source remains hidden in rock below the Pacific. The effects remain uneven across land and sea. Between those two realities stands the monitoring network, dense, technical, and continuous, making the sequence legible one signal at a time. In the first 72 hours after a major offshore earthquake, time itself becomes a region of study. The landscape has already been described. The sea, the coast, the shaking districts, and the observing networks are in place. Now attention stays strictly within the bounded early interval that follows the main shock, the short span during which agencies issue repeated updates. Emergency workers decide where to place effort, and scientists watch the sequence reveal its first stable clues. This period is important not because it contains certainty, but because it concentrates consequence. Many of the most useful observations about a sequence arrive here, while many of the most difficult public decisions must also be made here. The first minutes are marked by compression of action. Automatic systems process the earthquake. Alerts are sent. Railway systems may halt or slow. Municipal offices begin checking communications, shoreline exposure, road access, utilities, and reports from communities. Coastal warnings are treated with seriousness even before the full sea response is measured. In homes, hospitals, schools, ports, and industrial sites, people move from shock to procedure. The body experiences the event as sudden movement. Institutions experience it as a cascade of priorities. The first part of the 72-hour window is therefore not calm inactivity, even if the scientific language around it remains careful. Within the first few hours, the central task is stabilization, rescue, medical transport, fire prevention, shoreline caution, and infrastructure inspection begin at once. At the same time, the earthquake sequence itself is still active. Aftershocks are expected in almost all large earthquakes, and in the immediate period they are not background noise. Each one has the potential to interrupt inspection, renew fear, damage already weakened structures, and complicate decisions about movement and return. In an offshore event east of northeastern Honshu, this early interval also includes repeated checking of sea conditions because even when observed, tsunami heights remain limited. Harbour currents and oscillations may persist longer than the first visual impression suggests. By the end of the first day, information begins to separate into two kinds. One kind concerns direct impact, which roads remain open, which slopes are unstable, where utilities have failed, whether ports can function safely, and whether shelters or municipal facilities are needed. The other kind concerns sequence behaviour, how many aftershocks have occurred, where they cluster, how their sizes compare with expectation, and whether the early rate of activity is rising or falling. These two forms of information are linked. A district with moderate initial damage may remain under strain if the aftershock rate stays active. A harbour that avoids major sea damage may still face disruption if repeated shaking keeps work suspended. The first 72 hours hold these two timelines together. This is why the interval is described as vital. The word does not suggest drama for its own sake. It reflects the practical reality that decisions made in this window have outsized importance. Authorities must decide when evacuation remains necessary, when transport can resume, when crews can enter damaged zones safely, and when public messaging should emphasize caution over reassurance. At the same time, scientists must avoid saying more than the data allow. They can estimate probabilities. They can compare the present sequence with earlier ones. They can state that strong aftershocks remain possible. They cannot specify the exact time, place, or size of the next significant event. The first 72 hours are therefore vital because action cannot wait for perfect knowledge. Sleep is also altered during this interval, though quietly and often without public emphasis. After a strong earthquake, rest becomes shallow in many households and shelters. Every sound, every vibration, every passing vehicle can resemble the beginning of another shock. In coastal districts with long memory of tsunami disaster, the psychological burden of night can be heavier than the burden of daylight. Emergency workers, municipal staff, port operators, engineers, and residents all continue under incomplete rest. This matters because fatigue changes judgment. The early time window is not only a geophysical period, it is also a human one, in which repeated alertness presses against the ordinary need for recovery. Scientifically, the first 72 hours offer the clearest chance to observe the sequence before later background noise and broader adjustments make interpretation less direct. Aftershock locations are mapped as they arrive. Depth patterns are examined. The ratio between smaller and larger events is compared with familiar statistical behavior. Seafloor and coastal data are reviewed for evidence of ongoing marine hazard. Instrument corrections improve the estimates of magnitude and rupture extent. In a sequence described as unusual, this period is especially informative because departures from the ordinary short-term decay pattern often become visible here first. Not every apparent irregularity survives closer analysis, but the early days provide the richest view of the sequence while it is still near its point of release. Operationally, the window is also when systems are tested not by a single shock but by repetition. A network that works well for one earthquake must work again and again if the aftershock sequence stays active. Public attention can remain high through the first day, then begin to fray. Repeated alerts may become both necessary and burdensome. Local governments must decide how often to issue updates and how to keep guidance clear without sounding either alarmist or dismissive. The first 72 hours demand not only technical capacity, but steady communication. Too little warning invites risk. Too much unshaped warning can dull response. The interval is therefore a time discipline as much as a hazard period. In coastal and upland districts alike, this early window determines whether recovery can begin in an orderly way, or whether it must remain provisional. Engineers may inspect a bridge in the morning and return again after a strong afternoon aftershock. Fishing activity may remain paused even after the first marine warning is lowered, because the combined effect of uncertainty, current variation, and repeated shaking keeps conditions unsettled. Schools and public facilities may be opened selectively, not because one universal answer exists, but because the early days reveal which places are resilient and which remain vulnerable. Time, in this sense, behaves like a filter. It exposes what held, what shifted, and what requires patience. By the close of the 72nd hour, the sequence is rarely finished, but the first rough character of it is usually clearer. The direct emergency phase may begin to soften into sustained monitoring and repair. Or, if the aftershock activity remains unsettled, the atmosphere may continue to feel provisional. What matters in this section is not a promise about which outcome will occur. Observations indicate only that the first 3 days hold exceptional value for caution, measurement, and decision because this is when strong aftershocks remain plausible. Infrastructure remains freshly stressed, and the evidence needed for interpretation accumulates most rapidly. So this region of the story is time itself, bounded to the first 72 hours after the main shock. Within it, emergency action, public fear, scientific measurement, inspection, communication, and repeated uncertainty all coexist. The interval is short on a calendar, yet dense in meaning. It contains the first shape of the sequence, the first tests of resilience, and the first careful attempts to understand whether the earthquake is settling into an ordinary decline or something less straightforward. In that compressed early period, every hour matters because the Earth is still speaking in fresh motions, and society is still learning how to answer them. Within the first 72 hours, the aftershock sequence begins to show its own rhythm. This rhythm is rarely smooth. It is not a simple line falling at a constant rate. Even in ordinary earthquake sequences, clusters appear, pauses occur, and some hours feel busier than others. Yet scientists still speak of typical behavior because, over time, many aftershock sequences tend to decline in frequency after the main shock. The largest activity usually comes early, then the number of shocks gradually falls. In the present case, attention settles on the possibility that this decline is not unfolding in the most familiar way. Here, in this region of the story, the focus remains only on that pattern of recurrence, on the repeated breaking of surrounding rock after the main release, and on what makes the sequence seem unusual without turning uncertainty into drama. An aftershock is an earthquake that follows a larger main shock in the same general area because the fault system is adjusting to a changed stress state. The main shock does not simply end motion. It redistributes stress through nearby rock and along adjacent parts of the fault. Some places are brought closer to failure, others are relaxed. The result is a sequence of later earthquakes that belong to the same broad event. Aftershocks can be tiny, too small to be felt except by instruments, or strong enough to cause fresh damage. Their sizes, timing, and locations vary. But their existence is one of the most familiar features of large earthquakes. What makes a pattern seem unusual is usually not the mere presence of many aftershocks. Large earthquakes often have many. The concern grows when the timing, clustering, or size distribution differs from what is most commonly expected in the early days. Sometimes activity drops and then rises again. Sometimes strong aftershocks arrive after what feels like a quiet interval. Sometimes the shocks spread across a broader zone than first anticipated. Sometimes the smaller events do not dominate the count as strongly as they do in a more ordinary decay. None of these signs alone proves that something extraordinary is unfolding. They simply narrow attention onto the short-term behavior of the sequence itself. The usual reference point for aftershock decline is a statistical tendency in which the frequency of shocks decreases with time after the main event. This tendency does not promise a neat downward staircase. It describes an average behavior seen across many sequences. In real time, the pattern can look messy because earthquakes occur in bursts. 1 hour may contain many shocks, the next far fewer, and the next a renewed cluster. That roughness is part of normal seismicity. An unusual pattern begins only when the departures from the expected decline appear persistent enough that scientists cannot dismiss them as ordinary fluctuation. Even then, they remain careful. Early impressions can change as more complete data arrive. In the present sequence, the sense of irregularity comes from the possibility that the aftershocks are not settling as quickly or as simply as the early expectation for a major offshore event might suggest. Observations indicate active recurrence in the early period and a need for close watch rather than quick reassurance. That wording matters. It does not mean a larger earthquake is imminent. It does not mean the sequence is breaking the rules of seismology. It means the familiar decline may be interrupted by clustering renewed bursts, or stronger than expected events within the same short interval. The pattern asks for patience in interpretation. There is a physical reason why such irregularity can happen. The main shock changes stress unevenly. It does not press equally on every nearby patch of rock. Some parts of the fault may have been close to failure already and need only a slight additional push. Others may require more time, perhaps because fluid pressure changes slowly or because the local frictional conditions allow a delayed response. When this happens, the aftershock rhythm may appear uneven at the surface. A quiet period can be followed by renewed activity, not because the sequence has started over, but because different patches of the stressed region are responding on different timescales. Sequence clustering is one of the most important features here. A cluster is a tight grouping of earthquakes in time, in space, or both. Clusters can make the sequence feel restless even when the long-term trend still declines overall. For people experiencing the event, a cluster means repeated interruption, repeated alarm, repeated inspection, and repeated uncertainty. For scientists, a cluster may indicate that a specific patch of fault or surrounding rock volume is continuing to adjust. In a typical sequence, clustering exists, but it is often nested within a broader decline. In a sequence described as unusual, the clustering may remain prominent enough that the broader decline is harder to recognize in the first days. Size also matters. Most aftershocks are much smaller than the main shock. This is one reason the largest aftershock in a sequence often attracts particular attention. A relatively strong aftershock can renew concern not only because it is felt widely, but because it suggests that substantial stress remains available in the surrounding zone. Even so, scientists resist reading too much from one event alone. A large aftershock may fit comfortably within known statistical behavior. An unusual pattern is more often a property of the sequence as a whole than of any single shock. It lies in the repeated rhythm, the persistence, and the spatial arrangement of activity rather than in one dramatic number. Another reason caution remains high is that human perception responds strongly to irregular recurrence. A perfectly steady decline would be easier to live with, even if it remained active. Irregular sequences are harder on attention and sleep because they deny the body a clear sense of settling. A quiet morning can be followed by a sharp evening shock. A day that seems calmer than the last can still contain one event strong enough to restart fear. In this way, an unusual aftershock pattern is both a scientific observation and a lived experience. It affects the interpretation of data and the rhythm of daily decision at the same time. Still, uncertainty must remain narrow and honest. Scientists can say that the sequence appears to require careful monitoring because its early behavior is not the simplest expected decline. They can compare the event with prior offshore sequences and refine their estimates as more earthquakes are recorded. What remains uncertain is whether the pattern will smooth out into a more ordinary decay after a little more time, or whether irregular clustering will continue long enough to reshape the near-term hazard picture. The data in the first 72 hours are rich, but not final, so this section stays entirely within the aftershock rhythm itself. The main shock has already passed, yet the surrounding crust continues to answer it in repeated releases. These releases may still belong to a familiar statistical world, but their short-term shape appears uneven enough to command attention. The pattern is unusual not because it abandons known earthquake behavior, but because its recurrence seems less tidy, less quickly settling. and more dependent on clustering than the public might expect from an ordinary decline. In that restless rhythm, the sequence shows its next inner layer. Once the aftershock pattern begins to stand out, science turns from description toward measurement. This is the region where the sequence is no longer viewed only as a cluster of repeated earthquakes, but as a statistical object that can be counted, compared, and cautiously projected. The work here is precise but limited. Scientists do not ask the sequence to reveal a schedule, because earthquakes do not offer one. Instead, they examine rates, magnitudes, locations, and changes through time in order to estimate what kinds of aftershocks remain plausible over the coming hours and days. In this inner layer of the story, the main subject is not the fault itself, but the mathematical boundary between what the data can support and what they cannot. One of the first measurements concerns decay rate. After a major earthquake, the number of aftershocks usually declines with time, but the speed of that decline can vary. Researchers compare the observed sequence with statistical models built from many earlier earthquakes. These models are useful because they offer a baseline. If the present sequence produces more shocks than expected in a given period, or if the fall in activity is slower than usual, that difference becomes part of the hazard picture. Yet the comparison is never exact. Two sequences of similar size can still behave differently because the underlying fault system, stress field, and rock properties are not identical. Statistics provide guidance, not a template that reality must obey. Another key measurement concerns magnitude distribution. In most earthquake sequences, small shocks are far more common than large ones. This tendency is strong enough that seismologists can estimate whether the observed balance between small and larger aftershocks looks ordinary. If a sequence produces relatively fewer small shocks than expected, that may mean the catalogue is incomplete in the first hectic hours because some weak events were missed in the noise of stronger shaking. It may also indicate a real difference in behaviour. Distinguishing between these possibilities is part of the scientific challenge. The raw count of earthquakes is never enough by itself. Researchers must ask which events were actually detectable at each stage of the sequence. Detection changes through time. Immediately after a strong main shock, instruments may record a dense overlap of signals. Small events can be hidden within this crowded wave field, especially when one aftershock follows closely after another. As the sequence spreads out, more of the weaker events become easier to identify. This creates an important statistical limit. The apparent rise or fall in small earthquakes may partly reflect improvement in visibility rather than a true change in the Earth. Scientists correct for this as best they can, but in the early period some uncertainty always remains. An unusual pattern may therefore become clearer only after the catalogue is cleaned, relocated, and reviewed more carefully. Forecasting in this context means probability, not prediction. This difference is central. A forecast can estimate the chance that one or more earthquakes above a certain size will occur in a defined interval. It cannot specify the exact hour, the precise hypocenter, or the certainty of a single next event. For example, agencies may state that strong aftershocks remain possible over the next few days, or that the probability of another large event is elevated compared with normal background conditions. Such statements are scientifically meaningful because they describe relative risk. They are not promises that a particular shock will happen. The distinction protects both accuracy and public trust. The public often hears probability as if it were hidden certainty. Science must resist that misunderstanding. A low probability does not mean impossible. A high probability does not mean guaranteed. In the present offshore sequence, Official guidance notes that the chance of a larger regional event has risen above its usual background level. That matters because the baseline is ordinarily low, so even a modest relative increase deserves attention. At the same time, the absolute probability remains well below certainty. This is why authorities advise preparedness without claiming that a larger earthquake is imminent. The numbers support caution. They do not support a timetable. Statistical limits also appear in spatial forecasts. Scientists can describe the region where aftershocks are most likely based on the main rupture area and the surrounding redistribution of stress, yet they cannot draw a sharp line beyond which no further activity will occur. Aftershocks often cluster near the main shock, but some occur at the edges of the stressed zone or along nearby structures affected by the same change in force. This means maps of expected activity are always zones of higher and lower likelihood, not sealed boundaries. In a sequence that already appears uneven, this uncertainty becomes especially important because renewed activity may arrive at a segment that seemed quiet a few hours earlier. Another limitation lies in sample size. During the first 72 hours, scientists are working with a short record. Even if many aftershocks have occurred, the time span itself is brief. Short records are vulnerable to overinterpretation. A burst of activity may look like a trend when it's only a temporary cluster. A lull may seem reassuring even though it falls well within ordinary variation. This is why careful analysts rarely make strong claims too early. They update their view as each new portion of the sequence arrives. The pattern becomes more reliable not because the Earth grows simpler, but because the dataset becomes less fragile. Model choice matters as well. Different statistical frameworks emphasize different aspects of the sequence. One may focus on decay rate, another on magnitude distribution, another on the probability of a larger aftershock given the observed early behavior. These models are not rivals in a simple sense. They are tools suited to different questions. In a current event, scientists often compare them rather than relying on only one. When several approaches point in the same direction, confidence grows. When they differ, uncertainty must be stated plainly. That is not a weakness. It is part of responsible science, especially in the first days after a major earthquake. Communication becomes delicate in this region because the numbers are abstract while the consequences are concrete. A family deciding whether to sleep in a damaged home does not think in statistical distributions. A port authority deciding whether to resume operations must still convert uncertain probabilities into practical thresholds. This is why scientific caution is paired with operational advice. The science describes the range of plausible outcomes. Policy and emergency management decide how much risk is acceptable under those conditions. The two are connected, but they are not the same thing. So this section remains within the domain of statistical limits and uncertainty. Here the sequence is counted, fitted, compared, and projected in probabilities rather than certainties. The models can show whether the aftershock rate appears slower to decline, whether stronger events remain plausibly ahead, and whether the current pattern differs from the most familiar early behavior. They cannot say exactly when the Earth will move next. That boundary is the center of this region. Science can narrow the field of risk, but it cannot turn an active fault into a clock. After the sequence has been counted and its uncertainty described, attention moves inward again, into the stressed rock around the rupture itself. This is the region where the main shock leaves its mark on neighbouring faults and fault patches, not by direct visible breakage at the surface, but by changing the internal balance of force in the crust. An earthquake does not release stress everywhere equally. It reduces stress on some parts of the fault that have already slipped. while increasing it on nearby sections that now bear a greater share of the load. In this section, the focus remains entirely on that transfer of stress through the surrounding crust, on the invisible redistribution that helps explain why aftershocks appear where they do, and why some areas become more sensitive in the hours after the main event. Stress, in this context, means force applied within rock over an area. Crustal rock is never free of it. Tectonic plates push, pull, and grind past one another continuously, and that long motion creates a regional background of stored force before the earthquake. Parts of the offshore fault zone east of Miyako are already under compression because the Pacific plate is descending beneath northeastern Japan. The main shock releases some of that stored energy where slip occurs, yet the release is not a simple emptying of strain from the system. The crust behaves more like a loaded structure in which movement at one point changes the balance elsewhere. Some places are eased, others are tightened. This redistribution can be imagined, carefully, as a shift in tension across connected but uneven material. When one patch of the fault slips, the surrounding rock must adjust to the new geometry of displacement. Neighbouring areas may now be pushed closer to their own breaking point. This is why aftershocks do not simply repeat the exact motion of the main shock at the exact same spot. They often appear around the edges of the rupture zone, above it, below it, or on nearby structures linked through the same stress field. The main shock creates a new mechanical landscape, and the aftershock sequence is one of the first visible maps of that new landscape. Scientists often distinguish between static stress change and dynamic stress change. Static stress change refers to the lasting redistribution of force after the fault has slipped and come to rest in its new position. Dynamic stress change refers to the temporary but sometimes powerful effect of seismic waves passing through surrounding rock during the earthquake itself. Both may matter. The main long-term pattern of aftershocks is often associated with the static changes left behind by the rupture, yet the travelling waves can also disturb nearby faults, especially ones already close to failure. In a complex offshore subduction setting, the two effects may overlap in ways that are difficult to separate fully in the first days. The edges of the main rupture are especially important in this region. Inside the area that slipped most strongly, some stress may have been relieved. Along the margins, however, force can concentrate. These margins act like transition zones between the part of the fault that moved and the part that did not. Such boundaries are mechanically awkward places. They may host repeated smaller failures as the crust tries to accommodate the contrast in displacement. This is one reason aftershocks commonly ring the main rupture rather than filling it evenly. The sequence outlines the stress concentration left behind at the edges of the main release. In the present offshore earthquake, that redistribution likely extends through a three-dimensional volume, rather than a single thin plane alone. The plate boundary is the central surface of motion, but the surrounding crust above and below it also responds. Rock masses bend slightly, compress, relax, and shear as the fault changes position. Existing fractures, minor faults, and rough patches along the interface may all feel these changes differently. A patch that was stable before the main shock may become unstable after even a small increase in local stress. Another patch may remain quiet because the main shock has reduced the force acting on it. The aftershock pattern therefore becomes a selective record of where the new stress field encourages failure and where it suppresses it. Stress transfer also helps explain why the next 72 hours remain so important. The redistribution is immediate, but the crust does not always answer at once. Some failures happen within seconds or minutes. Others occur after a delay because the rocks require time to adjust, or because fluid pressure and frictional conditions evolve after the initial rupture. A quiet interval does not necessarily mean the stress field has settled. It may simply mean that the most responsive patches have already failed while others are still nearing their threshold. In an unusual aftershock sequence, these delayed responses may be especially relevant because they can produce renewed clusters after an apparent pause. This does not mean that every nearby fault has become equally dangerous. Stress transfer is directional and uneven. The geometry of the main rupture matters greatly. If the fault slips in one direction, some neighbouring sections may be loaded while others are partially unloaded. The orientation of nearby faults matters as well. A fault that is aligned with the new stress field may be encouraged toward failure, while another at a different angle may be pushed away from it. This is why seismologists study not only where aftershocks occur, but how their fault motions compare with the main shock. Similar mechanisms can suggest continued adjustment on the same broad structure. Different mechanisms may indicate that the transferred stress is activating related but distinct faults in the surrounding crust. The crust of northeastern Japan offshore is well suited to such complexity. It contains the main subduction interface, the descending slab, crustal faults in the overriding plate, and irregular structures inherited from earlier tectonic stages. Stress does not move through this setting as if it were an even block of stone. It passes through layered, fractured, and heterogeneous rock. Some volumes are stronger, some weaker, some more saturated with fluids, some more brittle. The stress transfer from a major earthquake therefore produces a pattern that is physically structured, even when it appears scattered on an earthquake map. The map is not random. It is the visible result of mechanical differences inside the crust. There is also a limit to what stress transfer can tell on its own. Scientists can model how the main rupture should have changed force on nearby fault patches, but these models depend on estimates of slip distribution, fault geometry, and rock properties that are never perfectly known in the early period. The calculations can identify areas where stress likely increased, and these areas often correspond broadly with aftershock zones. Still, the match is seldom exact. Real rock is more complex than any early model. For this reason, stress transfer is best understood as a framework for explanation rather than a precise forecast of every next shock. What it offers is physical coherence. It explains why the sequence does not end with the main shock. It shows why aftershocks cluster around certain parts of the rupture, and why an unusual pattern may arise when multiple patches respond on different timescales. It also reminds scientists that the earthquake is not a single break, but a reorganization of forces across a wider crustal system. The stress field after the main shock is a new condition, and the crust is still adjusting to it. So this section remains wholly inside that altered stress field. Here the earthquake continues not as one finished event, but as a redistribution of force through the surrounding rock. Some places are eased, others are pressed closer to failure. The edges of the rupture become especially active. Delayed responses remain possible, and the aftershock sequence traces the new mechanical balance left behind by the main release. In this deeper region of the story, the Earth is no longer being counted from the outside. It is being understood as a loaded crust learning, unevenly and under pressure, how to settle into a new state. Within the change stress field, the next inward layer is the geometry of the fault itself. Stress does not act in empty space. It acts on surfaces, bends, rough patches, and linked segments of rock that have particular shapes and orientations. In this region of the story, attention rests on those shapes. The question is no longer only where force is increased, but how the architecture of the fault guides the sequence that follows. A major earthquake offshore from northeastern Japan does not occur on a perfect flat sheet. It unfolds along a fault system with curvature, segmentation, and variation in slip. These geometric features matter because they help determine where rupture begins, where it slows, where it stops, and where aftershocks gather afterward. A fault is a fracture or zone of fractures in rock along which movement occurs. In a subduction zone, the central fault surface is the plate boundary itself, where the descending oceanic plate meets the overriding side. This boundary is broad in geologic terms, but the earthquake rupture occupies only part of it at any one time. That part has dimensions, edges, and internal variation. Some patches slip strongly, others move less. Some remain nearly still during the main shock even though they lie close to the rupture. The fault is therefore not only a surface of motion, it is a patterned surface whose uneven behavior leaves a clear signature in the aftershock sequence. One of the most important geometric ideas here is segmentation. A segmented fault is a fault broken into sections that are connected but not identical. These sections may differ in roughness, friction, angle, or prior stress history. A rupture can move across one segment easily, then slow at a boundary, or stop there altogether. Sometimes a later earthquake breaks an adjacent segment that did not fail during the first event. In the present offshore setting, segmentation offers one possible explanation for a sequence that appears less tidy than the public might expect. If the main shock releases strain on one part of the boundary, but leaves neighbouring segments only partly adjusted, the aftershock pattern can become uneven and persistent along those internal borders. Fault angle also matters. In the subduction zone east of Miyako, the plate boundary dips downward beneath Japan. Dip means the angle at which a fault surface inclines into the earth. A shallow dipping thrust fault spreads motion across a broad contact, and the distribution of that motion can vary with depth. Slip may concentrate in one depth range while tapering above or below it. This affects where stress builds after the rupture and where later earthquakes are most likely to cluster. If the main shock occupies only a limited portion of the dipping plane, then the regions up dip, down dip, and a long strike may each respond differently. A long strike means lengthwise along the fault, tracing its horizontal extent. Each of these geometric directions offers a different path for continued adjustment. Rupture behavior is shaped by roughness on the fault surface as well. Real faults are not polished planes. They contain protrusions, bends, scars from earlier motion, and zones where different rock types meet. These irregularities can act as barriers or anchors. A barrier is a place where rupture slows or stops because the conditions resist continued slip. An anchor is a patch that remains locked more strongly than its surroundings. Around such features, stress can concentrate. After the main shock, the sequence may gather along these rough structural boundaries because they mark places where the fault did not release strain evenly. An unusual aftershock pattern can therefore reflect not only the amount of stress in the crust, but the shape of the surfaces receiving that stress. Slip distribution is another geometric clue. Slip means the amount of movement that occurs across the fault during the earthquake. In a large event, slip is not the same everywhere. One area may move several meters, another much less. Seismic inversion, which is the method scientists use to infer the pattern of slip from wave data, often reveals patches of stronger and weaker motion across the rupture. These patches are sometimes called asperities when they represent stronger locked areas that fail in a concentrated way. The details of slip distribution matter, because aftershocks often cluster around the edges of high slip patches rather than at their centers. The fault geometry and the slip map together define a new internal landscape of contrast. This helps explain why earthquake maps can look scattered even when the underlying process is organized. If a rupture ends irregularly, bends around a rough patch, or skips across a segment boundary, the resulting aftershocks may form arcs, streaks, or offset clusters. To the eye, these patterns may appear messy. Mechanically, they reflect the shape of the fault system. In the offshore subduction setting, three-dimensional geometry can make this effect stronger because the fault plane descends beneath the coast, while related structures branch into the overriding plate and down into the slab. A sequence that seems unusual in time may therefore also be complicated in space, because the rupture occupies a geometrically complex environment. The early days after the main shock are when this geometry begins to emerge more clearly. At first, the source is represented by a location, a depth, and a mechanism. As more aftershocks are added and more waveform data are analysed, the internal shape of the rupture becomes easier to infer. Clusters may outline segment boundaries. Depth layering may suggest where the rupture was strongest and where it faded. Variations in focal mechanism among aftershocks may hint at nearby structures responding to the same stress change. None of this yields a perfect picture at once, but the geometry of the fault begins to show itself through repetition, the same way a submerged ridge is gradually revealed by currents tracing its contour. There is, however, an important limit. Fault geometry does not dictate every detail of the sequence. Rock properties, fluid conditions, and local friction also matter. Two segments with similar shape may behave differently because one is weaker, wetter, or closer to failure. Still, geometry provides the framework within which those other factors operate. It decides where rupture can travel, where it is likely to hesitate, and where stress contrast will be concentrated after motion stops. In a major offshore earthquake, understanding the fault's shape is therefore one of the most useful ways to move from raw observation toward physical explanation. For the current sequence, this means the unusual aftershock pattern may reflect not just a general redistribution of stress, but a rupture that interacted with segment boundaries, rough fault patches, and an uneven slip field along the subduction interface. Some areas may have released strongly and become quieter. Others may lie at the margins of high slip where the fault remains mechanically awkward and prone to further adjustment. The sequence, in this view, is tracing the architecture of the fault as much as it is tracing the passing of time. So this section remains fully within the geometry of rupture. Here the earthquake is shaped by dip, segmentation, roughness, and uneven slip across a broad offshore fault plane. The main shock does not break a simple surface. It moves across a structured boundary whose internal features help organize what comes next. Aftershocks gather where edges, bends, and contrast remain unresolved. In this deeper region, the event begins to look less like a single violent instant and more like a patterned interaction between force and form inside the Earth. Beneath the geometry of the fault lies the material character of the crust itself. Faults do not move through empty mathematical surfaces. They move through rock with temperature, composition, porosity, fracture history, and changing strength. In this region of the story, attention narrows from the shape of the rupture to the properties of the rock surrounding it. These properties matter because they influence how stress is stored, how slip begins, how aftershocks persist, and why some parts of the offshore source region remain active after the main release while others grow quiet. The sequence is still unfolding in the same general place east of northeastern Japan, but here it is understood through the materials that hold and transmit the strain. The crust in a subduction zone is layered and varied. On one side is the descending Pacific plate, made of old oceanic crust and the uppermost mantle beneath it. On the other side is the overriding plate beneath northeastern Japan, built from older crustal blocks, sediments, volcanic materials, and faulted rock masses shaped by a long tectonic history. Between them lies the plate boundary, a contact zone where pressure, friction, and deformation remain concentrated. Each of these materials responds differently to stress. Some are strong and brittle, meaning they fracture suddenly when pushed beyond their limit. Others deform more slowly or distribute strain over a broader zone. The aftershock field develops within this material contrast. Temperature is one of the most important controls on rock behavior. In the shallower and cooler part of the crust, rock tends to fail in a brittle way. Brittle failure means the rock breaks rather than flows. Earthquakes mostly occur in this brittle regime because sudden rupture requires stored elastic strain to be released quickly. Deeper and hotter regions often deform more gradually, bending or flowing over time rather than breaking in sharp events. The main shock east of Miyako occurs at a depth where brittle failure is still possible, and the aftershocks reflect continued adjustment within that mechanically active zone. If the rupture had occurred much deeper and hotter, the sequence would likely look different because the surrounding rocks would not store and release stress in the same way. Rock strength is also uneven across the source region. Strength, in simple terms, is how much stress a rock can bear before it fails. Some patches of the plate boundary and nearby crust are stronger because they are colder, denser, or more firmly locked. Others are weaker because they are fractured, altered by fluids, or made of materials that slide more easily. A major earthquake often reveals this contrast indirectly. Stronger locked patches may host concentrated slip when they finally fail, while weaker surrounding areas may respond through smaller repeated adjustments. The unusual aftershock pattern may therefore reflect not only how much stress is present, but how mixed the surrounding material strength remains after the main rupture. Fracture history matters as well. Rock that has broken many times is not the same as rock breaking for the first time. Old fractures, healed veins, fault gouge, and crushed zones leave behind mechanical weakness. Fault gouge is the fine, broken material produced by repeated grinding along a fault. It can act very differently from intact rock. Some gouge-rich zones may slip more easily. Others may lock under certain pressure conditions and then fail abruptly. In an active subduction setting, the plate boundary and nearby crust contain many such inherited structures. The aftershock sequence may be using these older weaknesses, not creating every path from the beginning. The present pattern is therefore partly a response to a long history of earlier strain stored in the rock fabric. Another important property is rigidity, which describes how strongly a material resists being deformed. More rigid rocks transmit seismic waves differently, and may accumulate elastic strain differently from less rigid ones. This affects both the main rupture and the sequence that follows. A rigid patch may store more stress before breaking, while a less rigid neighbouring zone may absorb some deformation without a large shock. The boundary between these materials can become a place of contrast after the main event. Aftershocks may gather there because the redistribution of force is crossing from one mechanical environment into another. The sequence, in this sense, is tracing boundaries not only of fault shape, but of material response. In the offshore region east of northeastern Honshu, sediment also plays a role near the plate boundary. Marine sediments carried into the trench and deformed along the margin can create weaker and more complex layers within the interface zone. Some sediment-rich areas may allow smoother sliding at certain times, while others may compact, strengthen, or trap fluids in ways that alter fault behavior. The exact effect varies from one segment to another. This is one reason neighbouring patches on the same broad subduction boundary can behave differently during and after a large earthquake. Material variation along the interface gives the rupture a patchwork character, and the aftershock sequence often reveals that patchwork more clearly than the main shock alone. The persistence of smaller earthquakes after the main event may also be linked to differences in how quickly materials relax. Some rock volumes adjust rapidly once the largest stress is released. Others continue to fail in small increments because their internal fractures, grain contacts, and local pressure conditions keep them near the edge of instability. This does not require a new large force each time. It can happen because the materials themselves have been left in a delicate state after the rupture. A zone of broken or highly stressed rock may continue to shed strain through many small events, giving the sequence its lingering texture. At the same time, there are limits to how confidently material properties can be mapped during the first days after an earthquake. Scientists infer these properties from seismic velocities, prior geologic studies, laboratory experiments on rock behavior, and the patterns of the earthquakes themselves. They do not see the rock directly at the scale of each fault patch. This means the explanation remains careful. Observations indicate that the offshore crust includes strong contrasts in temperature, rigidity, fracture state, and sediment content, and these contrasts likely help shape the aftershock persistence. It remains uncertain exactly which material boundaries are most responsible for each cluster in the current sequence. Even with that limit, the broad picture is clear. The fault does not cut through uniform stone. It passes through a varied mechanical environment where cold oceanic crust, altered sediments, fractured boundary material, and the rocks of the overriding plate all meet under compression. A sequence that seems irregular in time may become more understandable when viewed through this material diversity. Different rocks fail differently. Different layers hold stress differently. Different weakened zones respond on different timescales. The aftershock field is therefore not only a map of force, it is also a map of material contrasts inside the crust. So this section remains within the properties of the rocks beneath the offshore source. Here the earthquake is shaped by temperature, strength, rigidity, sediment, fracture history, and the mixed mechanical character of a subduction boundary. The crust is not a single substance. It is a layered and altered environment in which some zones break suddenly and others continue to adjust in smaller steps. In that material complexity, the unusual aftershock pattern finds another explanation. The Earth is not settling through one kind of rock alone, but through many, each with its own way of holding and releasing strain. Within the varied rocks of the offshore source region, the next inward layer lies at the contacts where slip actually begins and resists. Here the sequence is governed by fluids, friction, and failure at the fault surface and within the fractured rock around it. This is a smaller scale than broad stress transfer and a more intimate scale than fault geometry. The concern is no longer the overall shape of the rupture or the general strength of the crust, but the local physical conditions that decide whether two rock surfaces remain locked or begin to move. In this region of the story, the unusual aftershock pattern is explored through the hidden interactions of pressure, fluid-filled pores, grain contact, and resistance along the fault. Friction is the force that resists sliding between surfaces in contact. On a fault, friction does not act like a simple and constant brake. It depends on pressure, roughness, temperature, mineral composition, sliding speed, and the presence of water or other fluids within the rock. Two fault patches under similar tectonic stress may behave differently if one is dry and strongly interlocked while another contains fluid-rich fractures that reduce the effective grip between surfaces. This difference matters because an earthquake begins when the stress-driving motion exceeds the frictional resistance holding the fault in place. After the main shock, many nearby patches may sit close to this threshold, and small changes in local conditions can decide whether they slip. One of the most important local controls is pore fluid pressure. Pores are tiny spaces in rock and sediment, and when they contain fluid under pressure, that pressure can push outward against the surrounding material. In effect, high pore pressure partly supports the load that would otherwise clamp the fault surfaces tightly together. When that happens, the effective normal stress, meaning the force pressing the fault shut, is reduced. A fault with lower effective normal stress can slip more easily even if the total tectonic force has not increased much. This is why fluids matter so strongly in earthquake mechanics. They do not create the tectonic stress, but they can change how close a given patch is to failure. In a subduction zone, fluids are abundant in geologic terms. Oceanic crust carries water within minerals and sediments into the trench and down into the plate boundary environment. As pressure and temperature change with depth, some of that bound water is released into surrounding fractures and fault zones. The movement of these fluids is not simple. Some escape upward, some become trapped in low permeability layers, meaning layers through which fluid cannot move easily. Where fluids are trapped, pressure can build. In the offshore source region east of Miyako, such pressure variations may help explain why some fault patches respond immediately after the main shock, while others fail later in clusters. A patch may not require a large new stress if the fluid conditions are already weakening its resistance from within. Friction itself can also change during and after slip. Many laboratory experiments show that some fault materials weaken as sliding begins. This means the fault becomes easier to move once motion has started. In a main shock, such weakening can allow rupture to spread rapidly across a patch that were previously locked. After the main shock, smaller zones may continue to weaken and fail in shorter repeated bursts. Other materials behave differently. They may strengthen after small displacements, or respond more gradually to stress. The details depend on mineral type, grain size, temperature, and the condition of the contact surface. These differences help create an aftershock field that is active but uneven, because the fault is made of many local frictional environments rather than one uniform sliding surface. Failure at this scale often begins in small patches before spreading. A local grain contact breaks. A tiny rough projection on the fault gives way. A narrow fluid-rich fracture opens or slips. These microscopic and mesoscopic changes can link together until a measurable earthquake occurs. In the early days after a main shock, many such patches may exist near their limit, because the larger rupture has already disturbed the balance of force and resistance around them. The unusual pattern in the current sequence may therefore reflect a fault zone full of local patches that are only marginally stable, each responding according to its own pressure and frictional state. Some fail quickly, others wait, some produce only very small shocks, others link into larger aftershocks that are widely felt. Another important process is fluid diffusion, the gradual movement of pressured fluid through fractures and pores over time. This process is slower than the passage of seismic waves and slower than the instant redistribution of static stress, but it can matter in the hours and days after a major earthquake. If high-pressure fluid migrates into a nearby fault patch, it can reduce the effective clamping force there and encourage failure. This offers one possible explanation for delayed aftershock clusters that appear after a lull. The fault may not be receiving a new tectonic push from outside. Instead, conditions within the damaged rock are quietly evolving until resistance falls low enough for slip. Such behavior remains difficult to prove directly in real time, but it fits both theory and observations from some well-studied sequences. The damaged rock surrounding the main rupture is often called a fault zone rather than a single fault plane because motion is distributed across a fractured volume. Within that volume, permeability, meaning the ease with which fluid can flow, may change suddenly after a large earthquake. New cracks can open. Old cracks can be sealed by shifted grains. This changing permeability affects where fluids move and where pressure is trapped. As a result, the physical environment of the fault may still be reorganizing during the first 72 hours. The aftershock sequence is therefore not only a response to a changed stress field, it may also be a response to a changing internal hydraulic state inside the fault zone. Yet caution remains necessary. Scientists can infer the likely importance of fluids and friction from the style of the sequence, from rock studies, and from general understanding of subduction zone mechanics. They cannot observe every pressured pocket or every sliding grain contact directly during the event. The explanation is strongest at the process level, rather than at the exact location of each shock. Observations indicate that fluid-rich fault zones and variable frictional conditions are common in offshore subduction environments, and likely contribute to delayed and clustered aftershocks. It remains uncertain how much of the current unusual pattern is controlled by fluid migration, how much by purely mechanical stress concentration, and how much by the interplay of both. Still, this inner layer offers a powerful picture of why a sequence can remain active even after the main release. The fault is not merely a broken surface left behind by the earthquake, it is a living zone of pressured fluids, resisting contacts, fractured pathways, and local weakening. After the main shock, many parts of that zone may be left near the boundary between stability and failure. A slight rise in fluid pressure, a small drop in frictional resistance, or a tiny new crack can be enough to release another aftershock. The pattern then appears irregular at the scale of towns and maps, but at the scale of the fault it is a series of local responses to changing resistance. So this section remains within the intimate mechanics of the fault zone itself. Here the earthquake is shaped by friction between rock surfaces, by poor fluid pressure in tiny spaces, by gradual fluid movement through damaged rock, and by the conditions that decide when resistance gives way. The unusual aftershock pattern may owe much to these hidden processes because they operate on short distances and shifting timescales. In this region, the Earth is not only under stress, it is also wet in places, rough in places, tightly clamped in places, and ready to fail where pressure and friction fall out of balance. Deeper still, beneath the scale of fault patches and fluid-filled fractures, the earthquake resolves into the smallest units of breaking that can still produce measurable waves. In this region, the focus narrows to microfracture and the generation of seismic waves themselves. The crust no longer appears as large blocks or even as distinct fault surfaces, but as an assembly of grains, tiny cracks, and elastic bonds that store and release energy when stressed. The unusual aftershock pattern, when followed into this inner layer, becomes a record of countless small failures linking together, each contributing a fragment of motion that, when combined, is detected as an earthquake. A microfracture is a very small crack that forms in rock when stress exceeds the strength of the material at a local point. These fractures can occur at scales far below direct observation during an active earthquake sequence. Yet they are essential to understanding how larger ruptures begin and how aftershocks continue. Before a measurable earthquake occurs, stress concentrates at grain contacts and along microscopic flaws. When enough of these points fail and connect, they create a path along which a larger slip can occur. The process is not smooth. It is stepwise, irregular, and dependent on the local arrangement of material and stress. Seismic waves are produced when stored elastic energy is released as these fractures grow and link. Elastic energy is the energy stored in rock as it is deformed under stress. When the rock breaks or slips, That energy is converted into motion that travels outward as waves. There are different types of seismic waves, each moving through the Earth in its own way. Some compress and expand the material they pass through. Others move it side to side. In the context of this section, the specific type is less important than the principle. Every aftershock, large or small, represents a release of energy that began at the smallest scale of failure and expanded enough to be detected. In the period following a main shock, the crust near the rupture is often filled with a dense network of microfractures. Some were created during the main event, others existed already, but were brought closer to failure by the redistribution of stress. This damaged zone is mechanically weaker and more complex than intact rock. It contains many potential pathways for further failure. As stress continues to adjust, microfractures can grow, coalesce, and trigger new small earthquakes. In an unusual aftershock sequence, this process may remain active for longer than expected, or occur in bursts as groups of microfractures reach their thresholds together. The linking of microfractures is not uniform in space or time. In one volume of rock, cracks may remain isolated and fail quietly without producing a measurable event. In another, they may connect rapidly and generate a detectable aftershock. This uneven behavior contributes to the clustering observed at larger scales. A cluster of aftershocks may correspond to a region where microfractures are particularly dense, or where stress remains concentrated enough to drive repeated failure. A quieter region may simply lack the same conditions for linkage, even if it lies within the broader stressed zone. Wave propagation also carries information about these small-scale processes. As seismic waves travel through the damaged crust, they are scattered, absorbed, and modified by the complex network of fractures. This can affect how clearly events are recorded and how precisely they can be located. In the early period after a large earthquake, when the crust has been freshly disturbed, this scattering may be stronger than usual. It adds another layer of difficulty to the task of identifying and analyzing small aftershocks. The sequence is not only active, it is also being observed through a medium that has been altered by the main rupture. The persistence of aftershocks at this scale reflects the gradual release of remaining elastic energy. The main shock releases a large portion of the stored strain, but it does not empty the system. Residual stress remains distributed through the surrounding rock, especially in the damaged zones where microfractures have weakened the material. As these zones continue to adjust, they release energy in smaller increments. Each aftershock represents a local step toward a more stable configuration, though the path to that stability is uneven and may include periods of renewed activity. There is also a threshold effect at work. For a microfracture to grow into a measurable event, it must overcome local resistance and connect with neighboring fractures. This depends on both stress and material properties. Slight variations in pressure, friction, or fluid content can determine whether a fracture remains isolated or becomes part of a larger slip. This sensitivity contributes to the irregular timing of aftershocks. The system is close to a critical state, where small differences can produce noticeable outcomes. The unusual pattern may therefore reflect a crust that is finely balanced, with many regions hovering near the point of failure. At this inner level, the distinction between a small aftershock and a large one becomes a matter of scale rather than process. Both begin with microfracture. Both involve the release of elastic energy. The difference lies in how far the rupture spreads and how much energy is released. In the early days after a major earthquake, the conditions that allowed a large rupture may still exist in parts of the fault zone, but they are less likely to be met in full again immediately, more often. The system releases energy through many smaller events. Still, the possibility of a larger aftershock remains because the same fundamental process applies at all scales. Uncertainty persists here as well. Scientists cannot observe individual microfractures during an active sequence. They infer their behavior from laboratory studies, from the statistical properties of earthquakes, and from the way seismic waves travel through the Earth. Observations indicate that dense networks of small cracks form in damaged zones and play a key role in aftershock activity. It remains uncertain exactly how these networks evolve in detail during the first 72 hours of a specific event. The explanation is therefore general rather than exact, grounded in well-understood physics but applied cautiously to the present case. This perspective helps unify the sequence. What appears as a complex and sometimes irregular pattern of aftershocks at the surface is, at its core, a process of countless small failures linking and releasing energy within a stressed and fractured crust. The unusual character of the sequence may arise because these microfracture networks are especially active, unevenly distributed, or influenced by the earlier factors of stress transfer, fault geometry, and fluid conditions. The smallest scale of failure thus connects directly to the largest patterns observed in the days after the main shock, so this section remains at the level of microfracture and wave generation. Here the earthquake is no longer a single event or even a set of fault patches. It is a field of tiny cracks forming, linking, and releasing energy, each contributing to the sequence of aftershocks that follow. The crust adjusts not in one smooth motion, but through many small steps, each one sending waves outward. In this deepest mechanical layer, the Earth is quiet in appearance but active in detail, continuing to settle through innumerable small acts of breaking. At the innermost layer of the sequence, after the coastline, the shaking districts, the monitoring systems, the early time window, the aftershock rhythm, the statistical limits, the stress transfer, the fault geometry, the rock properties, the fluids, the friction, and the microfractures have all been examined. What remains is the scientific meaning that can be drawn from the event as a whole. This is not a separate physical region in space, but the deepest interpretive region inside the subject itself. Here the task is to gather only what the observations support and to leave uncertainty intact where the Earth has not yet yielded a complete answer. The current offshore earthquake east of northeastern Japan becomes, in this final section, a case study in how a subduction boundary releases strain, how an aftershock sequence can depart from the simplest expected decline, and how modern seismology balances knowledge with restraint during the first crucial days. The first clear meaning of the sequence is that the offshore margin east of northeastern Honshu remains a deeply active tectonic environment shaped by the continuing descent of the Pacific Plate beneath Japan. That broad conclusion is not new, but each major earthquake renews it in concrete form. The plate boundary is not a background condition that can be acknowledged once and then ignored. It is an active mechanical system that keeps loading, releasing, and readjusting across timescales far longer than human planning cycles. The present earthquake confirms that this margin remains capable of producing strong offshore thrust events, whose effects extend from deep rock to coastal decision-making within minutes. The second meaning lies in the behavior of the early sequence itself. Observations indicate that the aftershock pattern deserves attention because it does not appear to settle into the most straightforward short-term decline without complication. The sequence shows the familiar features of a large subduction zone earthquake, yet within that familiar frame it seems to include clustering, persistence, or renewed activity sufficient to keep scientific and public caution high. This matters because it reminds both researchers and the public that typical behavior in seismology is statistical, not mechanical fate. A sequence can be recognizably ordinary in its tectonic setting and still irregular in its short-term rhythm. From a scientific point of view, this is important because it strengthens a lesson already well established in earthquake research. The Earth does not produce one universal style of aftershock decay. Instead, each sequence is shaped by the interaction of many layers of control, the geometry of the rupture, the uneven redistribution of stress, the strength and temperature of surrounding rock, the presence and movement of fluids, the frictional state of fault patches, and the small-scale damage left behind by the main event. The current sequence does not overturn that understanding, it deepens it. It shows, again, that complexity in earthquake behavior arises naturally when many controlling processes overlap within one active fault system. Another meaning concerns the value and the limits of modern observation. Japan's dense networks of seismometers, intensity meters, coastal gauges, and offshore systems make it possible to identify unusual features in near real time. Earlier generations could have described shaking, damage, and perhaps the broad outline of the event, but they could not have traced the evolving aftershock rhythm with such precision. The present sequence demonstrates how much richer the scientific picture becomes when a subduction earthquake is observed across land and sea with dense instrumentation. At the same time, it shows that even the best monitored sequences do not yield exact prediction. Data can refine probabilities, map clusters, and narrow explanations. They cannot convert an active crust into a schedule. This point has practical meaning as well. Public communication after a major earthquake must live inside uncertainty without being paralyzed by it. The present event illustrates why warnings in the first 72 hours remain so careful. Scientists can say that the chance of another strong aftershock is elevated above background. They can say that the offshore source, the sequence behavior, and the known history of similar events justify continued caution. They cannot say precisely when the next important shock will arrive, or whether the sequence will settle abruptly or gradually. The scientific meaning of the event therefore includes a civic lesson. Good hazard communication is not the removal of uncertainty, but the disciplined explanation of what uncertainty allows and what it does not. The sequence also reinforces a quieter truth about earthquake science. Large earthquakes are not isolated objects. They are transitions within longer chains of tectonic loading and crustal adjustment. The main shock is only the largest and most obvious part of that chain. Before it, stress accumulates silently. After it, redistribution continues through aftershocks, fluid shifts, microfractures, and repeated small releases. The scientific meaning of the present event is therefore not contained in its magnitude alone. It lies in the way the earthquake reveals the subduction system as a living structure, always balancing force and resistance, always partway between locked stability and sudden motion. There is also a methodological lesson here. Seismology advances not only by studying the largest disasters, but by studying the detailed behavior of individual sequences, especially when they seem to depart from ordinary expectation. An unusual aftershock pattern, if confirmed through continued analysis, becomes valuable because it tests models of decay, stress transfer, and fault interaction. It asks whether existing frameworks are sufficient or whether some parameters in this region need to be reconsidered. Such a sequence may sharpen estimates of how offshore subduction events near northeastern Japan behave in the first days after rupture. Even if the broader theory remains sound, the local calibration of that theory may improve. Yet restraint remains essential. It remains uncertain whether the unusual features now drawing attention will still appear unusual once the full sequence is relocated, catalogued and examined over a longer interval. Early impressions are powerful because they shape public feeling and emergency response. But science must let the sequence lengthen before deciding how exceptional it truly is. Some apparent irregularities soften when more small events are detected. Some strengthen when the catalogue improves. Some prove to be characteristic of a particular fault segment rather than rare in any universal sense. The honest meaning of the present event therefore includes uncertainty about its own final classification. What can be said with confidence is narrower and more durable. A major offshore thrust earthquake has occurred in an active subduction setting east of Miyako. The sea surface response, the coastal exposure, the inland shaking, and the first 72 hours all matter because they translate deep tectonic release into immediate human consequence. The aftershock sequence remains important because its early behaviour appears active enough to justify continued caution and close monitoring. The physical explanations for that behaviour are consistent with the established earthquake science: uneven stress transfer, segmented fault geometry, mixed rock properties, fluid effects, frictional variability, and ongoing small-scale failure in damaged crust. So the deepest interpretive region resolves into a calm but firm conclusion. The event does not suggest that earthquake science has failed. It suggests that earthquake science is doing exactly what it should do when the Earth behaves in a way that is familiar in structure but irregular in detail. It is measuring carefully, comparing honestly, warning without over-claiming, and allowing explanation to grow only as far as the data permit. In that sense, the sequence offers a final lesson in patience. The Earth speaks first through rupture, then through aftershocks, then through the slower work of analysis. What is known becomes clearer step by step. What remains uncertain is not a defect in the science, but a truthful boundary around it. The coast grows quieter as the hours pass, though quiet does not mean stillness. Far beneath the Pacific east of northern Japan, the rocks continue their slow adjustment, releasing here and there in small motions too brief to see and too deep to touch. Instruments keep watch across the sea, along the shore, and through the towns inland. Their traces lengthen into records, and those records settle gradually into meaning. In the first days after a major earthquake, certainty remains narrow, but the outline of understanding becomes steadier with each measured event. The broad boundary remains what it has long been, a place where the Pacific plate descends and the crust above it bears the strain. The main shock has already passed. What remains is the patient work of the Earth easing toward a new balance. Some of that work arrives as aftershocks. Some remains hidden in the change pressure of fluids, in the friction of rock surfaces, in the small cracking of damaged crust. None of it is hurried. None of it is theatrical. It is the ordinary seriousness of a restless planet. Along the coast, harbours, roads, seawalls, and slopes return slowly to routine under careful eyes. Inland, buildings, bridges, and rail lines are checked again and then checked once more. In laboratories and agencies, the sequence is counted, mapped, and compared with older ones. Observations indicate much. It remains uncertain exactly how the pattern will fade. That uncertainty stays within the calm frame of science, where caution and patience belong together. So the earthquake settles into memory not as one instant alone, but as a layered event, beginning in the wide Pacific margin and narrowing inward to stress, friction, and fracture. The surface grows calm first. The deeper adjustments take longer. Above them, night returns to the coast, to the hills, and to the sea. while the Earth below continues its slow, unfinished work.